Hello everybody, thanks very much for joining us for this talk today with Alan Szepieniec. He's going to be talking to us about Neptune Cash. I'm excited to hear everything that he's going to let us know about Mutator sets. Thank you, Alan.
Thank you. And it's great to be here at Parallel. This conference, series of conferences popped up on my Twitter feed a few years ago, and I've always been wanting to come. And now I finally have the opportunity, and it's been great so far. So I'm Alan. I'm with Neptune. Neptune is a new privacy-based blockchain. We are bringing ZK Starks to layer 1. Our Stark engine is called Triton VM. So much for the shilling. I'll do more shilling at the end of this presentation. But what the rest of this presentation is going to be about is our architecture for scalable privacy called Mutator sets. And it's not specific to Neptune, so if you want, you can integrate this into another solution. You can even use it for things that don't do money to begin with. So this is the overview, and I'm not going to return to this slide. This is just to orient the audience beforehand a little bit. I'm going to motivate the problem, and then I'm going to articulate good and bad solutions, and then show in the basic instruction how to do it as a first iteration, and then in our next iteration we're going to actually make it scale down there. And then there's some comparison and concluding words. So the idea is, if you want to do money on a public ledger, you need a UTXO set. You can also do accounts, but there's a... You can think of accounts as UTXOs. UTXO is just an account you use once. And as long as you can maintain the UTXO set is the entire reason why we are willing to pay the price of having a consensus mechanism in the first place. The UTXO set is the piece of valuable information that we want to have consensus about, because it contains the database of all coins that can be spent. And we want it to be current. We want everyone to agree about the state of the current UTXO set. And so we don't really care about previous states unless as a means to authenticate the current state. And in fact, using fancy zero-knowledge and succinct proof systems, we can actually forget about previous states as long as you commit to them. And the reason why the UTXO set changes is because every time you make a transaction, you take some coins out of the UTXO set and you destroy them. And the act of destroying coins, the act of destroying UTXOs, entitles you to create new ones, and you put the new ones back in. That's why the UTXO set changes. And this is where the problem comes in as well, because when you make a second transaction, you're going to take coins back out of the UTXO set, and if those coins are the same, as is indicated here by the color, the fact that those coins are the same is obvious to anyone who reads the blockchain. That gives them a trace, and that ultimately undermines privacy. So this is the core problem that we want to solve. We want to remove this trace while still having the means to authenticate transactions, or the means to determine which transactions are valid and which are not. So the idea, the whole reason why we are using this public UTXO set is because it's auditable. Auditability is pretty good. It's how you know that certain transactions are double spending transactions and should be discarded. It's how you know that there's no inflation. But unfortunately, as a result of having a public UTXO set, it's also bad for privacy. Now, if you use zero-knowledge proofs and make the UTXO set opaque, which you can do, and I'll explain how to do, they can still retain this auditability, but you can be private as well. So, starting from basically the same picture, let's articulate the ideal construction for achieving this. We have UTXOs in our UTXO set, but the UTXO set is opaque. So on the slide, I'm showing what's in there, but these are actually more like black boxes. Whenever we take something out, it turns into this circle. The circles go into transactions. The transactions destroy the circles, and the transactions produce squares. The squares go into the UTXO set. So every time you take something out, it's a circle. Every time you put something in, it's a square. And in the lingo we came up with, these are removal records, and these are addition records, because they record the removal and addition to the set. They are cryptographic commitments to the UTXO, and hiding, I guess, depending on who you ask, a cryptographic commitment is already hiding or not, but these are binding and hiding commitments, meaning that you cannot lie about the data they conceal, unless you can find a collision to a hash function or something like that. So, a mutator set is something that achieves this. It's a cryptographically authenticated data structure that allows you to put items in, take items out, all the while hiding the items that these operations pertain to, because the only thing that is visible from the outside is the publication of addition and removal records. What you should not be allowed to do is inspect those removal and addition records. They are, after all, hiding commitments. You're not allowed to remove non-members. If you could do that, that would kind of defeat the purpose of having a set to begin with. And you should not be allowed to link removals to additions. That's the property that you need for privacy. And then one last property, a property that's kind of difficult to achieve. We want it to be scalable. We want all the algorithms to be efficient. We want all the data stored by all the participants to be not too big. So here is the standard solution, it was the first iteration of privacy on cryptocurrencies. It's using decoys and nullifiers. And I'll get into why this solution is not preferable after explaining how it works. So in my lingo, we still have removal records and addition records, except in this, they're called nullifiers and notes. I think of it as a commitment to the transaction output. Other cryptocurrencies use different terminology still. Every transaction, it still consumes a bunch of nullified, or rather, it consumes a bunch of nodes and produces a bunch of nodes. But in addition to that, there's a proof, denoted by the word pi. This proof is key, because what it establishes is that in the list of all previous transactions, there was this one transaction output that maps under some publicly known deterministic function to this nullifier. And, by the way, this nullifier was not published before. Now, in order to prove this, and in order to verify it as well, you need access to two things. One is the entire list of transaction outputs, and the other is the entire list of published nullifiers. Fortunately, the list of transaction outputs you can compress using Merkle trees or Merkle mountain ranges or whatnot. That's not too difficult. But the entire list of published nullifiers keeps on growing indefinitely. You cannot compress it, you cannot truncate it. There's nothing you can do except store the entire thing, and by the way, it keeps on growing forever. This is why we don't like decoy and nullifier set solutions. We say they don't scale. Now, on to describing how mutator sets work. One key ingredient is Bloom filters, but I'm warning you, in the first iteration, of how mutator sets work, it's not scalable yet. The scalability only comes in afterwards. So, Bloom filters. The idea is we want to determine probabilistically, so with a reasonable certainty but not absolute certainty, whether an item belongs to a database. And we want to come to a reasonable answer with much less compute work than it takes to run through the entire database and test for membership naively. And so what we are going to do instead of running through the entire database is we're going to hash the item using k different hash functions. And every hash function gives us an index into a very long array of bits. And as we hash all the items in the database and we set the bits indicated thusly, we get an array of bits in which roughly half the bits are set, roughly half being the Bloom filter is operating at optimal capacity. And then we can test for membership very quickly just by hashing the item and looking at the indicated bits. If they're all set, then maybe the item is in the database. But if any one of these bits is not set, then we know for sure that the item is not in the database. And there's a probability expression, there's an analytical expression for the probability of getting a false positive. And the nice thing about this expression is that there are tunable parameters. We can make the window size very large, we can set the number of hash functions to something very small or something very large, depending on how you want it to work, depending on how many items you expect to accumulate. And as a result of tuning those parameters, we can make the false positive probability cryptographically small. At this point, we've turned an optimization to save compute work into a cryptographically authenticated data structure. So we're going to use Bloom filters for sure. Except, we're not going to use Bloom filters to track membership. We're going to use Bloom filters to track non-membership. Right, I forgot to say that Bloom filters, I just mentioned that the false positive probability can be made to be negligible, cryptographically negligible, but unfortunately they have a finite capacity because as you add more and more items, eventually your array of bits will become all ones and then you can't use it for anything anymore. So, the first step towards making use of this is to address the finite capacity problem. We are going to set bits in an active window that keeps sliding every so many iterations. And when it slides is determined by some timestamp. And this allows us to keep inserting items indefinitely because the active window can keep sliding and the new portion of the Bloom filter is always implicitly 0. And so since you know that the portions of the sliding window Bloom filter that have not been accessed yet are going to be 0 anyway, you don't have to store zeros. So you just have to store the portion that has been accessed. So it does introduce this timestamp, but in exchange you get unlimited capacity. So we're going to use this sliding window Bloom filter to track non-membership, or actually more specifically to track removals. And we're going to use a regular list of commitments to track members. This is the first iteration of the basic construction. So what happens when we want to add an item to the mutator set? Well, we hash it with some appended randomness, so as to ensure semantic security. And then we append it to the list. And the index at which we append to the list gives us the timestamp t. And then what happens when we remove an item? Well, suppose we want to remove this item. We can only remove it if we know the pre-image under that hash function. So that pre-image, which is a coin, hashes to this and gives us the timestamp. But simultaneously, we send this pre-image, this coin, using the same hash function to bits inside of the window determined by that timestamp. That gives us a sequence of absolute indices in this very long window, and we set those bits. There's one thing missing, which is you cannot broadcast this entire computation because you're leaking the thing that you don't want to be leaking. So you have to run it inside of a zero-knowledge proof. You have to prove, I know of a coin that hashes to this commitment, or that hashes to some commitment in this list, rather, and that hashes under a different hash function with this timestamp to these bits. And by the way, here are my bits. The bits are public. In fact, the bits, the indices of the bits are what make up the removable record. So why does this work? Well, we've already tweaked the knobs on the sliding window Bloom filter so as to ensure that the probability of false positives is negative. But since we're using this to track removals, the probability of not being able to remove something that wasn't already removed is negligible, which is good. So you're always able to remove something that was added integrally, except if you can find a collision to a hash function or something like that. And you can always add something to the list of commitments. So this is the basic picture, but of course it doesn't scale well because you have these huge arrays of digests and of bits, and they scale linearly with the number of items added or removed. And I'll address that later. For now, I want to point out that you can already analyze this construction from the point of view of security as well as from the point of view of privacy. The security I already articulated in crude terms. Here is privacy. The idea is we're not allowed to be able to link addition records to removal records. And yet, we do have this fuzzy timestamp because all of the bit indices live within a window. We don't know the exact demarcations where the window starts and where it ends, but it is a probabilistic indication. So we have a fuzzy timestamp coming from the removal record. And with the fuzzy timestamp, we can infer a distribution of plausible origins. This is something we can't really get around. The argument is rather this distribution is sufficiently wide to make privacy feasible. And so for a bunch of parameters that, in fact, we've chosen to use in Neptune, we can look at the entropy of this probability distribution. And how often do you observe probability distributions of entropy 3? That's corresponding to hiding behind 7, which is 2 to the 3 minus 1 decoys. On average, we observe an entropy of 5. That's hiding behind 31 decoys, 2 to the 5 minus 1. And plenty of times the entropy is in fact higher. Note that the entropy is never smaller than 3 because the batch size is 8. So if you want to increase the minimum entropy, you can just increase the batch size. You might have to tweak something about the other parameters, but the point is that there is some overflow of probability between batches, so you can't even identify which batch a given removal record corresponds to. Here's a question.
Yeah, you said W is the window size, V is the batch size. What's S and K?
S is the step size, and K is the number of bit indices coming out of the hash function. by the way, all of this is in the paper, and the paper is public. I don't think I have a link to it on the slides, but you'll be able to find it if you Google mutator sets. So here's a note about scalability. We can characterize how well this scales in terms of parameters, number of additions, number of removals. These are snapshots at the time that an item was added, and we can also look at the number of operations in between addition and removal. And in this picture, the basic construction is actually pretty terrible because we need to keep track of the entire array of added digests and the entire array of bits corresponding to removed items. And then every operation in the meantime, whether it's an addition or a removal, we basically also need to carry around data corresponding to that. But there's a tweak. There's a second iteration of this construction that basically solves this. And we can reduce everything to having a logarithmic complexity at the expense of having to keep track of witnesses. This would correspond to your Merkle authentication path or your membership proof in some kind of abstract accumulator. So there is work now. You have some string of cryptographic data that proves that you have a coin living in the mutator set, and you have to update it periodically. Now, the workload of updating it is also not too bad because it's logarithm, it's polylogarithmic, but it's there, it's not zero, and that's a trade-off. So, on to the scalable construction. First thing is we need Merkle trees. A Merkle tree is built up out of 2 to the k data items called leaves. And you build the Merkle tree by dividing it into layers, where each successive layer has half the number of nodes. And each node connects to 2 children, and the value of each node is the hash of the concatenation of those children. So if you do that, you end up with a single digest called the root. And if you want to authenticate the membership of any one of those leaves in the Merkle tree, then you first trace the path from the leaf to the root, and you identify all the siblings, and the set of siblings is called the authentication path. I'm afraid the projector is missing some colors, right? So this is the path, but what we really want is the siblings of all the nodes on that path. And with this information, with the authentication path and the leaf, a verifier can walk straight back up to the root and verify that the root is actually, the recomputed root is actually indeed the same as the root he already possesses. That's a Merkle tree. How do you build one? Well, the straightforward way is to put everything in memory and start hashing. What if you can't put everything in memory? One more thing, the height of the Merkle tree is logarithmic in the number of leaves. That's why we like Merkle trees. So, if we want to build a Merkle tree or calculate the Merkle root of a sequence of leaves that we cannot store in memory, then we need to find a way to compute this that is amenable to stringing. And so what we're going to end up doing is we're going to build a sequence of Merkle trees and combine them whenever we can. So think of this Merkle tree as infinitely long, and we're going to run over all the leaves, and whenever we can combine two trees of same height, then we combine them. So that way our memory cost is only logarithmic in the number of leaves that we've covered. And so if we follow this procedure, at some point we arrive in this state, and then a new leaf is appended, and lo and behold, we have two trees of the same height, so we merge them. Lo and behold, again we have two trees of the same height, and so we merge them. Again, we have two trees of the same height, and so we merge them. And if you follow this procedure every time, you start from a sequence of progressively smaller Merkle trees, and you end up with a new sequence of progressively smaller Merkle trees. And so if you keep track of the list of roots, which is the peaks, if you keep track of the peaks, then this functions as an accumulator that's very good for appending data items. And since it's composed of Merkle trees, you can prove membership to the accumulator, because your membership proof is just the same old authentication path. And so we're basically going to use Merkle mountain ranges to improve the basic construction of mutator sets. In the first step, we're going to replace the list of commitments with a Merkle mountain range of commitments. The AOCL, which is the append-only commitment list. And in the second step, we're going to replace the sliding window Bloom filter, the inactive part, with a, well, firstly we're going to divide it up into chunks, and then we're going to build a Merkle mountain range out of those chunks. That happens to the portions of the sliding window Bloom filter that lie before the active window. The active window itself is actually stored explicitly. And that's it. This is the construction. This is the most complicated slide I have. If you're going to take pictures, it should be of this. We can go on to comparing this to competing technologies. Now, the academic in me screams at how inaccurate this slide is, and it has to be inaccurate as a result of forcing everything into a subspace of comparable dimensions. So there is a lot of nuance that's missing from this slide, and I can't measure everything. But it's a good approximation towards making a comparison. We have a bunch of parameters. These parameters are tailored to currencies. So we have a total number of transaction outputs. We have total number of new transaction outputs after doing the first addition. We have the total number of unspent transaction outputs, which is different because some transaction outputs are spent. And then we have a batch size and a batch size. And the reason why we have two different batch sizes is because in the one case you use it once, and in the other case you keep mixing. And then in a non-UTXO based system, in an account-based system, we want to keep track of the number of users. This is a selection of dimensions that you might want to compare on, but there are obviously more dimensions that the slide does not have room for. And these are a bunch of privacy architectures. The decoy and nullifier set I already covered. Now, you can add accumulators and snapshots to the decoy and nullifier set, and I'd say you get something that's strictly better, but still not very scalable. And as far as I know, nobody's using that. Mimblewimble is using coin join and cut through, but I don't think they're doing anything in particular to obfuscate the graph of transactions. There are a couple of proposals that relate to mixing UTXOs, starting with QuizQuiz. Mutator sets is what Neptune uses, and then I came across a new construction, well, maybe not new, but I recently came across this construction using accounts where every account has the account is the encryption of your balance under an Elgamal crypto system. And so you can add an encryption of something, or you can add the encryption of 0, and the external observer cannot tell which one it was. So then we have a whole bunch of costs, and it's a shame that the red in the projector doesn't seem to be working, because anything that's linear in N or L is red. If it's U, it should be orange. And yeah, basically the decoy and nullifier sets, they both have red cells. And then in the question of trust assumptions, I don't think Wimble is entirely without trust assumptions, because if you publish your transaction, if you broadcast your transaction and the entire network sees it, then they'll be able to, well, they won't be able to see how much coins are being transferred, but they can draw the boundaries around your transaction, and that's supposed to be the whole thing that CoinJoin and Cut-Through obfuscates. So you can't broadcast your transaction. You have to merge it with other transactions before you broadcast. And so you have to send it to other people who might have transactions of their own in order for it to be combined. And at this point, you're trusting these other people not to broadcast your transaction. So I do think there are trust assumptions embedded in Wimble. And certainly when you're relying on a single mixing party, who's to say that they're not going to sell the permutation of this mix? So trust assumptions, we shouldn't ignore those. It's important to note that mutator sets don't scale quite as well as I would like. There is this factor U, which is a worst case U. This is, what is it, the cost of updating your witness scales linearly in the worst case with the unspent transaction, with the number of unspent transactions at the time that you inserted your UTXO. It's because every time one of those older UTXOs gets spent, you might need to do something to your own witness. Fortunately, vanishingly often, the work you need to do is on the order of log L, so it's not much work. It can be batched, and it can be outsourced. So, while in other places I drew the U in red, here I drew it in orange. One more thing I want to note is that this seemingly poor scalability of homomorphic accounts comes from the fact that we're comparing these architectures as standalone solutions. In reality, what Fern does is it lives on top of Ethereum, and so the cost of storing an entire database of users is far smaller than the cost of verifying the Ethereum virtual machine anyway. So we don't care about that there. All right, let's move towards a conclusion for this talk. In my eyes, the scalability and the privacy are orthogonal dimensions, and for some reason, existing constructions populate one axis or the other axis. And I think it's worthwhile compromising on privacy a bit in order to achieve better scalability, and likewise compromising on scalability for a bit in order to achieve better privacy. And I think that's what mutator sets exactly do. And the reason why is I don't really buy this tension. I don't think this tension is correct. They are orthogonal, but they're not mutually exclusive. And it's because you need scalability to foster crowds, to accommodate crowds. And you need crowds to make your privacy meaningful. So without scalability, you're not going to have privacy. And without privacy, who cares anyway? Beyond using this for digital cash, which is what Neptune does, you can use mutator sets for other things. And I came up with a couple of examples here. You can use it for an anonymous dynamic ring signature. So a ring signature is where we take a bunch of public keys and produce a signature that is valid under one of those public keys, but I'm not telling you which. Now, if the group of parties that this ring is between changes, usually you can tell who was a member of it and who is a member of it now and who got kicked out and who joined and so on. But if you want to hide those operations, well, you can use mutator sets. And then you have a signature that is valid under the public key associated with this dynamic structure, where people can join or where people can leave or get kicked out according to rules that can be verified independently. You can have anonymous revocable credentials. So this is where there's a database, or more abstractly, some kind of service being provided, and you need to prove that you have access to this database or service, like a membership card. And you don't want to leak your list of members. And you don't want to leak who gets kicked out, you don't want to leak who joins. Well, you want to be able to update this list of members. Well, you won't. You probably want to use a mutator set. And then this one thing that boggles my mind, and the reason why it boggles my mind is because all previous solutions for secure electronic voting used public key cryptography in one way or another. And, well, you could say we are cheating because we do use zero-knowledge proofs, but we don't use any hardness assumptions associated with public key cryptography. And so the reason why mutator sets work for electronic voting is because you can do a credential system, an anonymous credential system, you can do voting with any anonymous credential system, and the idea is if you are entitled to vote, you are a member of the set, then you have a credential which you can spend while you cast your vote. And the fact that you are a member should not be linkable to your vote. But you should not be able to vote twice. So after casting that vote, your membership should be revoked. Obviously, you can use a mutator set there as well. So, open questions. This is almost the last slide, I promise. The current construction uses two cryptographic ingredients. One is a hash function, and the other one is a generic zero-knowledge proof. And in fact, in the software we use Triton VM, and by the way, the only cryptographic ingredient on which Triton VM is based is the same hash function. So really, it's hashes all the way down. And so it's plausibly quantum secure, but there's no proof. I think a proof is within reaching distance, and if you're a master's student looking for a topic, have a look at this. And as much as I think this is a quantum leap in improvement, it's not perfect yet. I would like to be closer to both axes on the scalability and privacy front without compromising either. And so maybe some kind of number theoretic constructions can help there. All right, this is the last slide, I promise. You were listening to Alan Szepieniec, that's me. I'm with Neptune Cash, and we are bringing ZK starts to layer 1. That's Triton VM. The floor is open for questions.
Thank you, Alan. We have a question. Perfect. Hi, I have one question that's somewhat tangential, which is that, so I've been looking into like building things using accumulators and things like that too, but one thing I've always found out is that just like updating all the witnesses, like coordinating that process on the protocol is just incredibly annoying and tricky. Which is why I eventually just gave up and used like just the traditional like Merkle patrician trinomial structure and have full node storing. Like, what sort of like, how does Neptune generally solve this issue? How do we actually have all the users update their like witnesses unless they just watch the network for every transaction that comes in, which also doesn't scale?
The nice thing about Merkle trees is that the witness update operations batch really nicely. So you in the end, in the limit, you don't need to observe every single transaction. The larger the time span that you're trying to bridge, the fewer blocks in the meantime, relatively less blocks in the meantime do you need to observe to update your witnesses.
I see, but I guess somebody has to still tell you how to update your witnesses, and that person has to.
This information is available in the blocks.
Yeah,
So you just download logarithmically many blocks in the time span that you're trying to cover.
How would you know which blocks to download?
That depends on the concrete blocks, and the concrete blocks will say the information that you're looking for lives 2 blocks ahead of me, or maybe X many blocks ahead of me, and I don't know exactly what X is, but here's an estimate.
Yeah, but like, wouldn't that be very similar to just not doing this witness update thing at all, and just like looking up the latest state trie in an Ethereum like structure rather than using the accumulators?
To be honest, I'm not sure how the state trie works.
Oh, it's just like basically there you always just look up a full node to tell you like the path to the states, right? Or UTXO or whatever.
This is completely compatible with full nodes telling you exactly what your membership proof is, and the only thing you'll have to keep track of is the actual UTXO, the pre-image to the hash function. And the authentication paths, they can tell you what they were, and they can even tell you without you revealing any further information about the UTXO. So,
I suppose the advantage is that you don't have to update this path very often. Is that the idea?
you don't have to update the path very often, and you can outsource it to full nodes.
Makes sense.
Have another question? Can we go back to slide 14? So you have these Merkle trees and you have this Bloom filter. How can I test that something is not in the Bloom filter? Only by having the Merkle roots?
You want to prove that something is not in the Bloom filter, or rather you want to prove that bits are not set in the Bloom filter. And in order to prove that, you supply the authentication paths as well.
Okay. So I want to prove that some particular bits are not set in the Bloom filter. Okay, but then I have to supply a proof, and what if the Bloom filter is updated? Oh, but these paths don't get updated.
So these paths do get updated if UTXOs that predate your UTXO are spent.
Okay, it's in the future. Okay. By the way, if anybody wants, maybe we can go to the whiteboards in the hackerspace downstairs. We can continue this after. It's an interesting topic.
Sounds great.
Anyone has questions?
Down on the first row.
Can you go please to the slide with the speed assumptions, the scalability assumptions? One of the last ones. Yes, this one. Not clear why in the update time in Mutator says you have multiplication and not summation, because what you said about it, looks like it should be a sum, not multiplication.
No. Every time a UTXO that predates yours is spent, you have to do log L work.
All right. And who stores these proofs? Because you basically prune the state of the past. So you basically prune everything other than yours UTXOs. If you go to
Proof is overloaded. There's a zero knowledge proof and
Yeah.
there's authentication paths.
slide 40, the authentication path for the Bloom filter.
Right. Full nodes store all the authentication paths. If you don't want to run a full node, you have to store your own authentication paths and you have to update them from time to time.
By full nodes, you mean like then the full nodes have a linear scalability, right?
Yes, but they have that anyway because they're storing all blocks.
Okay.
More questions? Okay, I think it's over. Thank you, Alan, once again.